Okay, good morning. Welcome again to this Hipparcos Colloquia, to this new session. Before we start, as usual, let me tell you that next month we will have Pia Zurita from Hipparcos, from Theoretical Physics Department. She will be talking about topics related to particle physics. And today we have Daniele Oriti as a speaker. Daniele got his PhD from Cambridge in 2003, and well, first he stayed there for a couple of years, and then he went to Utrecht, and then to Perimeter Institute. After that, he became a group leader at the Albert Einstein Institute there in Potsdam, in Berlin. And after a few years there, I guess, he moved to Munich, again with a position as a group leader. And last year, he joined our institute and our department within the ATTRAE program. So I think the best thing that we can do now is just let him tell us what are his topics, his research topics, and in particular, what is space, what is time. So Daniele, whenever you want.
Yeah, thank you. So thanks for the introduction. I have many things to say, although a few answers to the questions. So brace yourself. We start. So I start with the very beginning of an essay by David Foster Wallace, which I think gives the idea already, once properly translated from literature to science. There are these two young fishes swimming peacefully and chatting in water, in very clear water. At some point they cross a very old fish, very wise, apparently wise, who tells them, asks them, so how is water today? And they keep going, then one looks at the other and said, what the heck is water? And David Foster Wallace basically goes on, and this is an excuse to start talking about going beyond our default settings and questioning even things that we take for granted. Well, quantum gravity is about questioning the most fundamental default setting of all, so space and time. This is not just a fancy thing, so we have a lot of stuff up there in space. Now imagine removing all of them, one by one. Well, this is what quantum gravity is about, to start with. Now, it doesn't look like that's much, but in fact, we now know that that itself is a physical system, and therefore it has a lot of structure. It does affect what all the other physical systems do, and is affected by what all the other systems do. So it's a basic structure in our approach, in our understanding. We have them, we use them. However, we know that this basic common sense way of understanding space and time, locating things in space and time, can be questioned, and it has been questioned, and it is now different in modern physics. So we model by common sense space as a continuum set of points, and spatial distances are computed assuming Euclidean geometry. We compute distances. Once we have distances between objects located at points in this continuum space, well, then from those distances we can compute any other geometric quantity. And time is basically an additional axis, an additional direction, but we model it and we conceptualize it in physics in the same way. In fact, that is true also in special relativity. But this commonsensical world is the Newtonian picture that has become common sense. It's not just, we built on common sense to have Newtonian physics. To a large extent, what we now take as common sense is the result of Newtonian physics. In any case, things go both ways. In special relativity, as you know, many things have changed from this picture, but in fact, from the point of view of GR, not so much. It's the same story. We have this absolute notion of space and time. The only thing, well, only, I mean, it's a big thing, but the main thing that changes is that we now know that our space distances and time intervals transform together, so it's better to model everything as a single entity, as space-time. But the fact that it sits there, it's not influenced by the other physical, it's not a physical system, it's not influenced by physical systems. We just use it to describe physical systems, has not changed. It does change in general relativity. To make the very, very long story short, in general relativity, the main lesson is that space-time becomes, in fact, a physical system. What we're using as if it was a purely mathematical structure, fixed and absolute, which is the metric to define distances in space, and then in time, and in space-time, now becomes a field, a dynamical entity itself, which has its own equations of motion, coupled to all the other physical systems, modeled as well in terms of fields. So we now describe gravity in terms of space-time geometry, which, if you think about it, is quite radical. It means that whenever you make a statement about the gravitational field, like, there is a certain orbit between two planets because there is a certain gravitational pull of one to the other, we are actually making a statement about the geometry of space-time. And vice versa. When I say the distance between me and that door is, I don't know, whatever, 15 meters, I'm actually making a statement about the gravitational field in this room, according to GR. So a deeper understanding of gravity in physics is now understood to be a deeper understanding of space and time. So general relativity works. That's why I take the main lessons and I try to keep them with me. It's the basis of our understanding of astrophysics and cosmology in all sorts of domains. Black holes, the evolution of the universe. In fact, once you realize that space-time itself is a physical system, has its own dynamics, well, then it becomes possible to consider space as indeed changing, affecting what the dynamics of all the other systems are, and you can have something like the Friedmann equations, an equation for space, for the geometry of space, depending on the distribution of matter in space, in the universe. And it's possible with that to explain what we see when we observe galaxies, going away from each other in any direction. And we understand it as being space itself that is expanding and somehow carrying with it all the physical objects, including the galaxies. And based on this idea, we now have a very detailed understanding of the history of the universe. So all of this is just to say that this is not just, we have a new interpretation of what gravity is. It has consequences in what we are able to understand, in what we see, in new things we are able to see, in fact, now out there, and in the physics we do. So let's look again at GR, and we realize that the way the theory is formulated, there are key structures. There is a topological manifold, first of all. There is some differential structure on top, which allows us to take derivatives and define the smoothness of our fields. Then there is indeed the continuum metric field, which is our gravitational field, and at the same time our key object for having geometry. And there are matter, gauge fields, and all the rest. These are the key ingredients in GR: dynamical continuum fields and a certain symmetry, diffeomorphism invariance. To make a very, very long story short, also here, what does it mean that we have diffeom invariance? It means that we can apply transformation mapping from points to points in the differentiable manifold. This transformation affects the fields defined at those points. So we have a transformation of fields. And our theory is invariant under such transformations. But the consequence is pretty radical of that, the consequence of this symmetry, the existence of this invariance in our theory. Again, I'm really cutting a very long story short, but the end point is that we realize that the differentiable manifold itself, with the points, the directions, and the coordinates, and all of that are unphysical. They're super useful. We use them all the time as physicists, but they're unphysical per se. We should be very careful. In fact, we shouldn't think of the manifold as space-time, as the set of points of the manifold as space-time points. Time is not a time-like direction on the manifold, and space is not a set of space-like directions on the manifold. And in fact, because of the same symmetry, the fields we routinely use, the metric field, the gauge fields, and the scalar fields, and all of that, are unphysical per se. Because if the points are unphysical, anything defined on a point cannot be itself a physical quantity. It's not invariant under our symmetry. So we want observables that are invariant under diffeomorphism to respect the symmetry structure of our classical theory. This is the so-called problem of observables in classical and then quantum gravity. Let me say in a few words what the problem is, because it's a key issue in any quantum gravity approach. It's not difficult to construct quantities which are invariant under diffeos per se. You can just take, for example, the volume density at a point in the manifold and integrate average over the whole manifold. You'll get a number, and that's invariant by definition and by construction, in fact, under diffeos, except it's not very useful. We don't measure this type of global quantities. We measure local physics. So the question becomes, what does it mean to have localized an object? What is a point, an event in space-time, if points on the manifold are not themselves physical because they're not invariant under diffeos? The general strategy that people use is to try to localize in space and time in a relational sense. And the idea is simply that you take some of the physical quantities like fields defined on your manifold to be for you the definition of time and space. So you use 4 fields, 1 as a clock and 3 as rulers, to define what you mean by a point in time and space. Their value is the event, with respect to which you define the localization of all the other dynamical fields. These physical fields that you use as a reference frame in the idealized regime in which they behave like perfect clocks, they don't interact with all the rest, and they don't have quantum fluctuations when you go to the quantum theory, they basically behave like coordinates. And that's the routine use of coordinates in classical physics. But from this point of view, you're supposed to take fields and invert their relation so that you can express them with respect to other fields you have chosen as clock and rods. And this is super difficult to do in general. But let me just flash an example. You can take the classical one-dimensional pendulum, the harmonic oscillator. We know everything about it. There's no fancy physics. But you can parameterize it. You can introduce an auxiliary fake coordinate, a one-dimensional manifold of parameters, and you define the position of your pendulum and the time of your pendulum, the one that you measure with your clock, as scalar fields, as fields on this auxiliary manifold. But then you will see that the system is not formulated in the most physical manner when you write it like this, because you will have one-dimensional diffeos, the reparameterization along this additional direction you introduced, which is a symmetry of the theory. When you construct relational quantities, only involving dynamical entities Q and T, and invariant under this reparameterization, you end up basically with the standard formulation of the harmonic oscillator. in which, well, there's only one thing you can predict. Q is a function of t, and both Q and t you measure. The idea is that GR is a sort of a parameterized field theory in the same sense, except that it's much more difficult than the pendulum to deparameterize. Anyway, so there are a number of structures in our understanding of space-time given by general relativity, the topology, the differentiable structure, the metric, the other fields, the construction of observables. All of this stuff has to be questioned and cannot be taken for granted. It's physics, right? We don't take things for granted. Okay, on the other hand, we have quantum mechanics and quantum field theory, which is the basis of all the rest of physics. And it comes with many profound implications and many unsettled interpretational issues. And so we cannot forget about that. First of all, because it's physics. Second, because it is as conceptually, foundationally interesting as what I just said about GR. So, what is the problem of quantum gravity at the conceptual, physical, and mathematical level? Before I tell you some results and some ideas that people are working on, what is the problem? What do we want to do? What is the motivation? Well, at first, at the conceptual level, we literally have a schizophrenic attitude towards fundamental physics as things are. We have two incompatible frameworks. They are incompatible, the one given by GR and the one given by quantum field theory, about what they say concerning space and time, on the one hand, and what they say about physics, all the other physical systems. Whatever you take as a key lesson from general relativity is not there in quantum field theory. Whatever you take as a key lesson in quantum field theory is not there in classical general relativity. So as physicists, we are forced to juggle from one conceptual framework to another, depending on the context. It sort of works to some extent, but I mean, it may not be really satisfactory, and it's a lot of pain. Especially when you feel that there should be, quantum effects on the gravitational side, and you cannot really control them, or you would like to take into account the physics of the gravitational field in a quantum field theory context, and you cannot. When we try to do it in a semi-classical manner, we just try to do a minimal extension of general relativity by adding quantum fields. Well, this framework is useful. We use it again all the time, but we know it cannot be fundamental for a long list of reasons. So the question remains, what are really space and time? It cannot be what GR says. It cannot be the end of the story. It cannot be what is in quantum field theory. What are they? And the quantum effects of the gravitational field are expected or suspected to be relevant in a number of physical situations, although they are quite extreme. But as far as we know, they are there. The center of black holes, the very beginning of the universe, where we have the singularities predicted by general relativity, which is basically telling us, sorry, I have nothing to say about that. Ask somebody else. Or, the physics of matter at very, very high energies, where it is implausible that gravitational effects are simply not excited, not relevant. All our paradigms for theoretical cosmology, especially when they concern the early universe, however successful they are in fitting observations and so on, they come with questions, issues that to some extent can be postponed because it's already hard, as our cosmologist friends know, to fit the observations. But they can be postponed, but they are there. And many of them ask for a quantum gravity type answer. I mentioned a number of examples. In inflation, well, depending on the scale of inflation, you may be dangerously close to the regime in which you actually do expect quantum gravitational effects. The inflaton field, how to put it, smells of an effective description in lack of a more fundamental explanation. In more exotic cosmological scenarios, it's probably even worse, in the sense that it's even clearer that you are assuming new physics of which you have no control. In bouncing cosmologies, in which there's no cosmic acceleration, there's no singularity of the Big Bang, but there is a bounce and a contracting phase ending up leading to the expanding phase we experience. Well, that bouncing regime is outside of current physics. We need a more fundamental theory to tell us what the physics of that bounce is. So you can make assumptions and keep going in your model building, but those assumptions will have to be supported by some, or tested or modified because of some more fundamental theory. In scenarios like emergent universe, in which you have a static phase and at some point there is a phase transition to an expanding one, even more, the physics of that transition is calling for a more fundamental theory. And there are questions about dark energy that I will return on, that I will touch again later. We mentioned black hole. We observe black holes, or something that looks very much like black holes. But we know that our understanding of their dynamics and their thermodynamics is lacking. And when we try to describe things staying within the framework of semi-classical physics, quantum fields on a black hole spacetime, we run into paradoxes that suggest that some of the fundamental principles of quantum field theory and or generativity will have to be replaced. Again, we need a more fundamental theory. And it's up for grabs, or up to debate, which of the fundamental principles will have to be replaced. Some people say it's unitarity, others say it's locality, or the equivalence principle, some maybe the continuum picture of space-time itself. So again, we need to go beyond generativity of quantum field theory. We need to go beyond our current understanding of space and time. But as I emphasized, they are really at the root of our model building, of our understanding of the world, and so it's very hard. I don't want to neglect that it's also a purely complicated mathematical, technical problem. You can even try to go, a lot of people do that. You just leave aside all the conceptual issues and maybe are not even now worried about the physical predictions. You have a classical theory, you try to turn it into some quantum theory the best you can. Well, it's damn complicated. Okay, now let me, again, before I tell you a bit of results and ideas, let me tell you what to expect. What is, regardless of the specific formalism, specific quantum gravity approach you like, and leaving also aside predictions, what do we expect? What should be true? Suppose you just take the classical theory, as well, at the very least, without trying to change anything else in physics, or any of my basic principles, I want to turn my classical fields into quantum objects, and the classical dynamical theory of GR into some corresponding quantum theory. That's how we proceeded for most of quantum field theories we know. Not all of them, in fact, but most. So that's what you're taught in the third year? Fourth year? Third year, I think. You take a classical scalar field theory, you quantize it. You have a certain mechanical system, you quantize it. Okay, let's quantize GR. Not the technical thing, we don't know how to do it fully, it's a work in progress, I'm going to tell you about, but what do we expect if we do that? Well, we should expect that the quantities that the classical theory is about, so space, time, geometry, volumes, areas, lengths, and so on, evolve probabilistically and become quantum observable. So they fluctuate. They have, superposition of different possible observational outcomes. And that means that no space-time notion, in particular localization, can be sharp. In quantum mechanics, only what you measure is sharp. That's normally only part of the information you have about the system. So there's no such thing in any future quantum gravity theory for a sharp notion of space-time and geometry. Now, this is the typical thing that when I say it, you're like, yeah, sure, I mean, quantum gravity. I got the idea that gravity is geometry, so quantum geometry, good. Okay, what is the area of this surface? You are about to say some number, whatever. I have no idea how long it is and how large it is, but whatever it is. No, in a quantum theory of gravity, to be rigorous, you should say, well, okay, I prepare my table in a certain state, and if it is an eigenstate of the area, then okay, I'm able to say that I measure it, I find a certain number. But that normally means that whatever is the conjugate quantity, that normally is going to have to do with the space-time evolution of that table, will be entirely uncertain. It doesn't look like a table, right? And if I prepare the table in a slightly more general state, then I measure the area, I get a number. Then I measure it again, I get another number. Then I measure it again in the same state, I get another number. Then I take a statistics and have a certain profile of the probabilities for all the different values. If this was not mind-blowing enough, think of other geometric observables, the distance between me and the door, or you and your friend, whatever. These are all quantum observables of the gravitational field. If that was not mind-blowing enough, think of causal relations. They had to do, they're basically another way of encoding geometry. The fact that I send signals to you, I speak in normal parlance, and you process the information, hopefully, and the fact that I can reach you with my voice is a statement that we are one in the light cone of the other. Is a statement about the causal structure of space-time. That fluctuates as well in a quantum theory of gravity. So causal relations are uncertain, fluctuating, probabilistically determined only. And the same geometric quantities I was mentioning, I told you, well, I'm in an eigenstate, I could be in an eigenstate of the area. What if the area as an operator has a discrete spectrum? What if that happens, and in fact it does happen in a number of approaches? What if the volume of this room has a discrete spectrum? What is left of the continuum intuition about space-time? Okay, so I mentioned the problem of constructing local observables, and I said, okay, it's very difficult even in the classical theory to deparameterize and to use physical frames only. Imagine the quantum theory, when the frame itself is a quantum system. You only have fuzzy clocks and fuzzy rulers. So you have all these structures in GR. Suppose they all go quantum. At which scale you should expect things to go quantum? You need quantum gravity. At which scale? You combine the fact that gravity should be relevant, so G Newton, it should be a relativistic theory, velocity of light should be relevant, it should be a quantum theory, so Planck constant should be relevant. There is one distance that come up combining the two, the Planck distance, 10 to the minus 33 meters. Now, there's only two things I want to say about this. So it's good, it's a good intuition. At that scale, we expect something to go wild. It's where we expect a new theory to be needed to describe new effects. Two things, however. First of all, 10 to the minus 33 meters is as distant in terms of scales to the smallest thing we can currently measure, I mean, indirectly, the size of a quark, then the size of a quark is to the human scale, which in my case is a meter. Okay? So it's the same orders of magnitude. Now, imagine how much new physics and biology and chemistry and sociology and ecology is in those 17 orders of magnitude. And now we are saying, well, we have to jump another 17 with the tools we have, GR and quantum field theory, the ones that work up to 10 to the minus 18. First cautionary remark. Second cautionary remark, how do we get to the idea of the Planck scale being the relevant one? We combine GR and quantum field theory. But I've just told you that GR and quantum field theory are exactly the theories we know cannot be the story, the full story. So it's a great indication of what could be happening, but it's a big assumption that that's the only thing that happens. The quantum gravity is only relevant there because GR and quantum field theory seem to say so. And so far I was in the paradigm we quantize space-time, or we quantize geometry, or we quantize gravity. Maybe that's not the story. We have learned a number of other things. We learned, for example, that general relativity can be understood or reformulated or derived as if it was a theory of space-time thermodynamics. There are a number of many open issues in that, but it's very suggestive. Maybe it's, that if that is true, if all the open issues can be fixed, it suggests that gravity, as we know it, is an effective theory like thermodynamics is, and there is some different type of degrees of freedom we should really be looking for that collectively look like gravity and geometry and all the other fields. This idea is also taken on board or suggested in a different domain, which is analog gravity in condensed matter systems, where people, like in the picture there, I think that's a photograph of a lab. You know, people go there and listen to this sonic hole in a fluid that behaves a bit like a black hole and like a curved geometry. But again, the suggestion is we can realize many of the features of gravitational physics in systems that are not really spatio-temporal, they're not really gravitational. Again, suggested that maybe those effects, what we understand as gravity, is just some effective description of something else. But again, this is radical. It means the space-time itself is a collective, emergent notion. There are many other suggestions going in the same direction, many other results that go in the same direction. None is a proof of anything, but this is a radical idea. The space and time themselves, as notions, even before being part of a physical model, they are emergent, collective, non-fundamental notions. Yeah. Okay, so maybe we have to take also on board this idea, but that changes a lot of the story, because now you have a situation a bit like in condensed matter. Quantum gravity will be then the problem of identifying microscopic constituents of space-time, but which are themselves not described in spatio-temporal language, because the notions of space and time have to be reconstructed out of them. It's a little bit like the problem of, I have the atoms, now I want to show you that a certain collective emergent behavior comes up from them in some approximation. So just like you have atoms or molecules and they condense, you get a fluid, and then in the standard, the effective description in terms of a liquid and hydrodynamics and whatever. Maybe similarly, now I had some other I have some difficulty finding pictures of the space-time atoms. I suppose you have little building blocks that somehow together collectively have a complicated dynamics. They condense, they form a quantum space-time, and then the standard classical space-time we know. Okay, now in the last 45 minutes, right? 10. Let's see. I tell you a bit more about the possible approaches, what people try to do and is trying to do to obtain the more fundamental theory. So, first of all, to clarify, in case you've been told otherwise, there is a variety of approaches to quantum gravity, a complicated landscape. There are many relations between them. Some of them are clear, understood, and they're being developed. Others are sort of neglected. Others are really hidden. And this is a typical quantum gravity conference with people discussing, with different sub-communities and chatting and, very, high intellectual endeavor. Sometimes these sub-communities, in fact, have more complicated relations. But in fact, if one looks at the science and not the sociology, there are many, shared issues and goals and technical tools sometimes are related, if not identical. And one should try to, exploit and develop further all these shared tools. Okay, one thing we agree is that you cannot postpone the issue. We tried to say, well, let's quantize GR as if it was a standard field theory, forget about all the lessons of GR, the more radical understanding of space-time, take a flat space-time, consider the gravitational field as a perturbation on top of it, treat it as a standard field theory. There's no issue with causal structure being fluctuating, there is a space-time there, flat. Then you will complete the theory, but at least let's show that this is quantum gravity. You do that, you arrive at the notion of a graviton, the particle of the gravitational field, only to show that it doesn't work. It's not a consistent theory, so it's great as an approximation, but not as a fundamental theory. So the lesson is that the quantum gravity vacuum cannot be the Fock vacuum of gravitons. A vacuum of space-time is not a flat space with no graviton, the Fock vacuum. The fundamental degrees of freedom are not the gravitons. Whatever they are, that depends on the formalism or the approach you follow, but they're not gravitons. At the same time, we want to recover this description because it's a good, effective field theory description of some quantum gravity effects. So this is a common goal by, as far as I know, the whole community. So, okay, you want to go beyond. There are two main options conceptually that you can try, that people have tried. One route, take GR and go quantum non-perturbatively. There are techniques to quantize field theories non-perturbatively, and people try to do it. So you keep the same type of degrees of freedom, the metric field or some variations of it, the standard matter fields, and you try to go quantum. Another possibility is that you first want to have a theory that works perturbatively, and since a simple gravity theory doesn't work, you add degrees of freedom or symmetry so that you have a good perturbative description of the story, which will then have to complete non-perturbatively. In the first category, you find, for example, canonical loop quantum gravity. You reformulate a bit the classical theory, and instead of using a metric, you use a connection, but it's still continuum fields. Then you quantize using the tools of gauge theories, because now you have a connection like in non-abelian gauge theories. So there are many more tools you can use. And there are many results. It's still work in progress, but there are many results. For example, the idea of discreteness of the geometric spectra is a rigorous result in that context, and it's still quite mind-blowing. People take a quantization route like in lattice gauge theory. So you discretize the manifold, you discretize your field, like the metric field, and then you try to define a path integral for the discrete theory. That is well defined, and the problem is to take a continuum limit, like in standard lattice gauge theories. And there are different ways of doing it. There are two main ways, if you keep the metric as the key dynamical variable. And string theory is an example of the other route. You have now a theory with more degrees of freedom, new symmetries, which is perturbatively well defined, with some caveat, but it's definitely better defined than perturbative quantum gravity. And then you try to complete it at the non-perturbative level. And that's where the real hard work is. The third option that I mentioned is that you don't quantize anything and you don't start with the usual space-time notions. You try to identify some new degree of freedom. And of course, we have no direct suggestion from experiments of what the new degrees of freedom should be. So it's hard, but people are looking at that. And in fact, the quantum gravity approaches I mentioned already start going a bit in this direction, even though they started from a more conservative perspective. For example, in canonical loop quantum gravity, although we started by quantizing the geometry, we end up with states which are spin networks, which are basically combinatorial objects and purely algebraic, combinatorial and algebraic. So we left the set of continuum fields, and we really use different structures. So continuum fields we had to emerge as collective quantities. And the same is in lattice gravity, and in string theories we have further suggestions that something like an emergent space-time description is the right one. Okay, there is more, and one that I mentioned is this groove field theory, which is, you remember the picture of building blocks being little simplices, pyramids or blocks. Well, you can write a quantum field theory for those blocks. Of course, it's more abstract, it's not defined on space-time, and where the quanta are such blocks, and you create, annihilate, and you have processes of scattering processes of these blocks, and the idea is that you treat space-time, you treat the universe as a sort of a quantum many-body system made out of these blocks, and you have to show that in some coarse-grained collective description, you can replace these blocks with some smooth field and the standard space-time description. So which other of the background structures in GR can become dynamical in quantum gravity? Geometry, okay. It should be already clear that that has to be dynamical, is the main point, and quantum. What about the other structures? These were the other structures I was mentioning, the dimension, the topology, the signature. Well, we have examples of calculations in some of quantum gravity approaches. Here is one example, in which the dimension of space-time, once you treat it as an observable, something that you deduce from some physical quantity you compute, you don't assume it, becomes dynamical. You treat, in some discrete approaches, like causal dynamical triangulations, you set up a diffusion process on your lattices, and then you ask how the diffusion progresses, how your milk spills, and or whatever other diffusion process you have in mind. And the way it propagates depends on gives you a notion of effective dimension. If there is a certain behavior, the effective dimension that the system sees is a certain number. And people see, by doing the calculation, that at large scales, you find the standard dimension you started from, like 4, like in our case. When you start going at higher energies, you end up with 2. So physics seems to be happening in an effective 2-dimensional world with respect to this type of physical processes in this quantum gravity approach and others. The signature. People study, in very simplified models, the evolution of the universe, and they find that instead of a Big Bang, you have a bounce. Then you look at the algebra of constraints that the gravitational theory has to satisfy, and they find that quantum gravity effects in a specific formalism modify a bit the algebra. You get this additional term, this beta term there. This is the algebra of the Hamiltonian constraint of your gravitational system. This would be the classical one. This is what you get after quantum gravity corrections. And the interesting thing is that, again, in this model, which is highly simplified, when you go towards the would-be Big Bang or Big Bounce, this becomes negative. And you would get a negative sign if the signature of space-time, instead of being Lorentzian, was Euclidean. So the suggestion is that, look, what quantum gravity does is that it changes, your universe evolves, then it turns on the quantum gravity effects, and effectively the very notion of evolution stops making sense. You have an effective Euclidean, dynamics because you have an equation, but it's not any evolution. So the signature can be affected by quantum gravity effects. What about topology? Well, there were very early ideas in the 80s about writing down a field for the universe that describes the creation and annihilation of universes. And the scattering processes are basically topology changing processes. You have a universe, it merges with another one, then it splits again. You look at the Feynman diagrams, and that's a manifold with a non-trivial topology. This is super formal. But when you go discrete, when you try to make the same idea working at the discrete level, you can realize it. That's exactly what you do in matrix models. You have the dynamical sum over topologies, produced as the Feynman diagrams of a field theory. In the higher dimensional case, in tensor models, and in the group field theory that I mentioned, where you have a theory of the building blocks, you ask what the Feynman diagrams are. The dynamical processes of the building blocks being merging, splitting, and scattering. Well, you find that the Feynman diagrams are lattices of the appropriate dimension of any topology. You have a dynamical sum over all possible topologies. Okay, and you can show also in the same approach, in this quantum many-body description of the universe in terms of these discrete building blocks, that if you take a hydrodynamic approximation, the hydrodynamic description can be turned into a description in terms of observables of a geometric meaning, say the volume of the universe. So you get an equation for such volume of the universe. So you have a cosmology, cosmological dynamics, as a rewriting in terms of specific observables of the hydrodynamic effective coarse-grained collective description of the quantum gravity building blocks. And you have a number of results. So you can show at this hydrodynamic level of approximation that indeed you have a bounce, not the Big Bang. That later when the universe expands, you have standard Friedman dynamics, so GR, a good classical limit. When the universe expands further, in some models, I don't want to make any claim of having solved any big issue, but in these models, you have an accelerated expansion, like a dark energy phase. Everything produced out of the quantum gravity interactions, quantum gravity features of the building blocks making up, constituting space-time and the universe. Okay, in the last 20 minutes, I will now say a few words about possible signatures and what we do in terms of phenomenology. There's only one message, and it's the message here. The rest is giving you a couple of examples of what people do. The message is there is such a thing as quantum gravity phenomenology. By now, it's a sub-community of people that work on that, very active with many, many directions. And so the problem is not, in my view at least, is not really anymore whether we can have experimental observational signatures of quantum gravity effects. We know we can. The question is also not to write down some tentative simplified phenomenological model that would predict such effects and can be constrained by the observations. That we know. The real problem, but maybe just because I'm a theoretician, is to connect those simplified models with which we do phenomenology to the more fundamental quantum gravity theories that people have developed. Okay? I give you a couple of examples. You know, in scenarios in which the Planck scale is really the key thing and it plays the role of a minimal length, or in scenarios in which the same scale enters in a deformation of the uncertainty relations, or in scenarios in which the same scale ends up deforming or leading to a violation of space-time symmetries like Lorentz symmetry, because Lorentz transformations are not usually understood as being compatible with some minimal length. I mean, you should always do length contraction when you boost. you end up contracting lengths when you boost, so there's no limit to how much you can contract. So when you introduce a minimal length, something has to change. Well, for example, dispersion relations will have to be modified, are modified. And modified dispersion relations are tested. And some models are just ruled out already. Scattering thresholds are modified. And so it can be, this type of models can be tested. Or you can have non-locality, so non-local terms due to this minimal length. Let me mention another couple of things. With gravitational waves, we can, for example, test any scenario, any theoretical scenario in which black holes are in fact replaced by objects, astrophysical objects, which are very, very similar to black holes, but they don't really have an horizon. And the horizon is a global structure in GR. So it's not really physical. I mean, it's not something that is beyond any doubt a physical thing. You need to know the whole history of the universe to determine that an astrophysical object develops an horizon in the standard sense of GR. So people have considered different options for how you can deform, modify a standard black hole solution of GR to have objects which are similar but not quite like black holes. And this leads to signatures in gravitational waves, potentially. All the stuff I said about quantum gravity modifying the early universe theoretical cosmological models, well, that is true. It leads to really questioning what happens at the Big Bang, which sits there in all these cosmological models unless it's modified in ways that we still have to control fully. It could be a bounce. It could be some sort of weird phase transition. I told you that if we have non-spatial temporal building blocks, and space-time only emerges in some approximation, maybe space-time emerges only one particular phase of the dynamics of the building blocks. And there is non-spatial temporal phases as well. And so you have a phase transition between the two. Maybe that's what happens at the Big Bang. And this is, again, something that is directly relevant for the type of quantum gravity model I was discussing earlier. We find a bounce in an hydrodynamic approximation. But the hydrodynamic approximation is an approximation. It may fail, and it may be, untrustable if the actual physics at the very early universe switches on all the quantum fluctuations of the underlying building blocks and leads to a phase transition instead. You don't trust hydrodynamics in that regime. All of this, in principle, gives signature in the CMB. There are a number of models. Okay, from this, here was a very nice video that shows that, especially if you take the emergent space-time point of view, you start being more and more suspicious of the effective field theory language. That starts looking to you. I put it in a very provocative manner so that the older people among you wake up, and because they're very upset and they start throwing things at me. The language of effective field theory, in which you have some new scalar field with some weird potential so that you can describe some observational phenomenon, I mean, it's all great, and it's very hard work to make things fitting and mathematically consistent and so on. So I don't want to disparage that. But it starts sounding a little bit like epicycles, adding epicycles to fit the orbits, complicated orbits that you observe. And here, I don't know if there is a way to show, I mean, there's a nice video you can find on YouTube of the orbital motion of an object in the sky that, it's very complicated, but you can describe it adding epicycles here and there until the orbit actually takes the form of Homer. And just as an example of how, if you're ingenious and technically skilled enough, you can fit observations even with tools that don't really look like fundamental ones. Okay, and in emergent space-time scenarios, one thing you question in particular of effective field theory is separation of scales. the very idea that quantum gravity effects are confined to very small scales in terms of distances or very high energies is based on space-time notions. In particular, I don't really know what energy is without a metric. So the moment I don't have a metric, and even because it fluctuates, or even more because it's just a collective notion, the more fundamental description is something else, I don't really know what the scale should be of quantum gravity effects. Now, we have example of this type of reasoning in condensed matter, by the way. But in our case, this suggestion could be, for example, that dark energy, although it's a very large-scale phenomenon from the point of view of effective field theory, could be of direct quantum gravity origin. And it's not just a wild speculation. There are concrete, I mean, it's a speculation, it's just not so wild. There are a number of concrete models, and I mentioned a number of possible descriptions of dark energy from the point of view of quantum gravity, large-scale modifications of usual physics. And I mentioned one more thing. I told you that you modify dispersion relations when you introduce the Planck scale. But if you have an underlying set of discrete constituents, another effect that may show up in dispersion relations is dissipation. You may have dissipative effects entering like imaginary terms in the dispersion relations due to the exchange with the constituents. All of this also can be tested. There are some results in the formalism I was mentioning earlier. Anyway, I conclude. It's unbelievable. We go and celebrate afterwards. I don't know when was the last time it happened. Simple conclusion, which of course is not a conclusion. Quantum gravity clearly is very much work in progress, and there are many, many directions in which it's progressing, more or less slowly or fast. I hope that one thing is clear, which is that already while we make progress, but definitely once we are there, it produces a radical reshaping of something that's the true foundation of our physical understanding of the universe. And no talk about theoretical physics and space-time can end without a quote from Einstein, I've been told. So this is a quote by Einstein and they said, okay, maybe, of course, I mean, at least since he gave many, many talks and interviews and people would ask him about anything, he was obviously asked about the possibility of replacing the space-time continuum with some other type of discrete or more exotic structure in light of quantum mechanics, for example. And he said, yeah, I mean, clearly in light of quantum mechanics, so in view of the molecular structure of everything, small scale, blah, blah, the introduction of a space-time continuum may be considered, not compatible with that. So maybe it has to go away. Maybe the success of the Heisenberg method, meaning quantum mechanics, points to a purely algebraic description of nature, and the elimination of continuous functions of the whole continuum picture of space, time, and fields and so on at the more fundamental level. However, so we have to give up the whole space-time continuum. And then he said, okay, what do I know? I'm just Einstein. So it's not unimaginable that human ingenuity will someday find methods which make it possible to proceed along such a path. At present, such a program looks like an attempt to breathe in empty space. So the point is that everything is very much in progress, but slowly, and I can tell you from experience, quite painfully, but still with some degree of conviction and enthusiasm on the good days, we are learning to breathe in empty space. Okay, thank you.
Okay. Thank you, Daniele, for a very entertaining talk and illuminating. So, questions now?
Hi, first of all, thank you for the talk. It was very interesting. I had a question. If I understood correctly, there are theories where space and time would not be a continuum and they would be discrete. How would that affect the math of the rest of quantum field theory when we take, say, a time derivative? Now we're working with objects that don't evolve in a continuum of time. So how would we change, or what would happen?
Okay, so it's not that there is a single answer, because it depends on how exactly you try to implement this idea of going discrete. So let me mention 3 ways in which people try to do it. One is that what is discrete is the spectra of geometric observables. So the formalism may still be in terms of fields in some way, but when you actually compute the spectrum of some observable, like the area of a table or a distance and so on, you find that it only takes discrete values. And that changes the propagation of, or the physics of other systems like matter fields and so on, because the geometric observables enter in matter observables. So the spectrum of matter observables may in turn be different. And then depending on the concrete case you take, that, I don't know, the discreteness of the spectrum may or may not have observable consequences in the physics of that matter system. That's one way. Another is a bit more naive maybe, is you really replace the continuum manifold with a lattice. And on that lattice, like we do in lattice gauge theory, or in general lattice field theory, you put discretized matter, so that there's non-zero values only on the nodes of a lattice. Then the continuum physics will have to be the result of some limit, some refinement, or some averaging over lattice size. And then the physics, so then you can say, well, this was just a regularization tool. In the end, is only the result of the limit, the continuum stuff that is physical, in which case, by construction, nothing has to change in the effective continuum physics from this type of discreteness. But you can take the point of view that those lattices are, in fact, the more fundamental degrees of freedom. And then any correction coming from not taking the full limit, or taking an average but then having dispersion around some particular average, will count as a physical effect due to the underlying discrete structure. And the third case that I can think of is a little bit like in condensed matter, where you have an atomic structure, but then in a particular regime, you have a fluid made out of the atoms or the molecules. Then you have quasi-particles or phonons moving on top of the fluid. And your question is then, do the phonons or the quasi-particles know about the atomic structure? How do they know that there is an underlying discrete thing and that the fluid is not the story, is not the full thing? Well, and then depending on the system, how the atomic structure influences and in which regime the dynamics of the phonons is different, but is the same analogy.
More questions?
Okay. Good afternoon, sir. First and foremost, thanks for the colloquial. I'm actually a first-year student of the physics degree, but I do look forward to knowing about these kind of fundamental issues. And out of pure curiosity, I've compiled 3 questions. I don't know if you would allow me to ask them. First of all, what would you say that has been the greatest breakthrough in the quest of the quantum gravity theory so far? Second, how far would you say that we are to fully reconcile general relativity and quantum mechanics given the advances in the quantum gravity theory? And third and last, given what you know and what you've shared, what would be your stance on the fine-tuning of the universe or the fine-tuning of space and time? Thank you.
So, sorry, the third question is, what would be?
Your stance on the fine-tuning of space and time.
I should bet about what happens at the beginning of space and time. You want me to give you my opinion?
Yeah, if you might. Thanks.
Okay. So the first question will basically just so about what are the big results and so on. Will just provide me with many more enemies in the community. Thanks. The second one will make me look like a fool by predicting when we will have the final theory. And the third one is the way to show that I'm also incompetent once I give a prediction and that clearly doesn't work soon. Okay, I have nothing to lose, right? So, okay, what are the big results? I would say that the very fact that now we have more than one highly incomplete but viable, meaning not already shown to be not working, approaches is the biggest result. Because that is I didn't do it. Because until 40 years ago, I mean, quantum gravity has a century and a half of history, almost a century of history. Until 40 years ago, there was no approach that seemed to be viable, working at least to some extent. Then in each of these formalism, one can pinpoint a key result that really builds the formalism. So from the perspective of each individual formalism, I can give you a list. You know, within string theory, this was a key result, this one was another key result, this is a key lesson. Within canonical loop quantum gravity, within group field theory, I tell you, look, this was a key result. All of these are incomplete. So I will not be as full as to say, well, this will stay as the key results in 40 years in the final theory. I can tell you what seem to be key results from each perspective. And if I now tell you which ones, then it's when I start making enemies, and so I won't do it. I can tell you in private, and then I have to kill you. Then the concerning, well, how long it will take. If you ask me in the good days, I would say, well, I mean, at least in this formalism, I see exactly what is the key step that it needs to be taken, and I have a good picture of what needs to take it, what is needed to take it, and so 10 years, 20 years. Outside, again, of a specific formalism, especially if I'm not an expert, I have no idea how long it takes. And then we should also be careful, what do we mean to have a final theory? We are physicists, right? So it's not just, okay, we solved the big issue, a big open issue in a formalism, so more or less is there. So we have the theory. Okay, we have a theory. You have to compare it with experiments. That may take more time. In any case, theories in general, but quantum gravity theories in particular, are severely under-constrained by observations. So even if we find 100 independent observations that corroborate a particular theory, in particular in the case of quantum gravity, okay, we can just say that this theory seems to be fine. in explaining a number of things we observe. But the theory will have many more aspects that we are not testing. So to get to the stage in which some of the effects predicted by some of the theories, once they've been formulated well enough to look solid, well, I'm an optimistic person in general, so I expect a couple of decades in the good days. If you ask me when the calculation doesn't work, then no, it will take centuries. And then what do I think happens actually at the Big Bang? Was that the question? What is my bet? I cannot hear really anything. So
He's mentioning the fine-tuning that you require in the early universe to get what we have. Initial conditions, I guess, is the issue.
okay. Okay. Again, in some formalism, the ones I work more on, the picture, I think, is something like there is a phase transition. For much of the physics, we can capture what happens after the phase transition that gives rise to a universe with a smooth geometry and all of that in terms of a bounce. And we are able, within the full theory, knowing more about the true ground state of the full theory, we can determine what is the initial conditions, a good initial state for fields and so on, closer to the very beginning, and then follow the rest of the evolution. So that's the sort of picture I would bet on, and I think is within reach in some optimistically short time. And the picture would really be like, we are fishes swimming in a bowl of water. We are handed the book of molecular physics. We do the calculations. We have a model. We see that our water is just the effective description in a particular phase of our system, of the system we are embedded in. And we find out what happened when actually the water was poured in the bowl at the beginning of our universe. I think this sort of picture is realizable. I hope I answered, otherwise I can answer in private again. Yeah.
Yes, good afternoon. I'd like to ask you a question. How much important is unitarity for you in all these approaches? I mean, if whatever theory you construct, including space-time degrees of freedom plus matter, does it have to involve unitarity? And if it doesn't, what would be the source for the loss of unitarity? I mean, because unitarity is at the basis of quantum mechanics. In other words, if you want to consider an emergent gravity model, and you have to describe it in terms of a Hilbert space, then unitarity is at the bottom of it. So would you rather sacrifice unitarity or any other thing?
Yeah, it's a very good question.
Thank you.
Okay, I tell you my feeling about that. So if we think of unitarity, the usual way we think about it in quantum field theory or quantum mechanics, meaning is the unitarity of time evolution, or the evolution of our system, then I see no reason to expect that something like that is present in any more fundamental quantum gravity theory. For the simple reason that I don't even know how to define it, because I don't have a preferred temporal direction with respect to which I would define unitary evolution or conservation of probabilities. So that notion of unitarity, my feeling has to go, and we have to learn to recover it, of course, in different regimes whenever is appropriate in terms of specific physical frames that we use as clocks. So as soon as we have a notion of time evolution, even approximate, then we should recover unitary evolution with respect to that clock, again, in some approximation. But in the general formulation of the theory or in a more fundamental regime, I don't expect the notion to be valid. If there is a more abstract notion of unitarity, having to do just with a Hilbert space formulation, but again, not tied to our usual understanding of what we mean by unitary evolution, conservation of probabilities, and so on, then that may be there in the fundamental theory if the mathematical language is appropriate. But then we would be forced anyway to have a drastic reinterpretation of what that unitarity means as a mathematical condition in the formalism, because of what I said earlier. But it's entirely open, I would say, and this is one of the key issues in the overlap with research on quantum foundations. People try to generalize quantum mechanics using less of the standard ingredients of quantum mechanics, are also interested in, can we drop unitarity? What would be a more general formulation of probability theories and so on? And that's where we overlap with quantum gravity.
So I think it is lunchtime for some of us. So thank you very much, Daniele, for your talk. And see you all in a month's time in this colloquium by Pia Zurita. Thank you.